For the recording, hello, I'm David. This is semester 1, 2022, and this is a revision seminar for Data Analytics 1. And we've got some faithful people, about the same number in the Zoom as there are face-to-face. I've gotten a couple of requests, and they've very graciously allowed me to look through the notes for a bit to make my decision of how I'm going to talk about this. So I've had a request to talk about probability, and so that's what I'm going to talk about. So the study of probability was invented for the purposes of, well, in Europe, it was invented for the purposes of studying insurance, because you wanted to know how likely it was for bad things to happen to people, which is how likely it was for you to have to pay them money. And it was also simultaneously invented for the purposes of gambling. In the Middle East, it was invented for the purposes of divination, of doing activities with dice or lots or things like that, for figuring out what Yahweh or Allah wanted you to do. And then in other cultures, it was very commonly used for games as well. Everywhere. So it's an old idea, but the notation that was has been created from it comes from Europe, because that's just the way it is, unfortunately. So people have understood probability a lot for a long time, but they've also understood that it's quite confusing. And it doesn't help that what has built up around it is a whole lot of notation, math notation, and a whole lot of terminology. So unfortunately, what it looks like when you study it from this end of history is having to learn all of those all at once. And so here we are. And it borrows some of its problems as well, because mathematicians invented it and then a couple of hundred years later figured out that there were some serious mathematical problems with the maths that underlies it, and so they had to fix all that later, and so you end up with some set theory notation borrowing over there. So there you go, that's a bit of history stuff. Yeah, last thing to bring is that human beings naturally, before you create mathematics, only have 3 sort of levels of probability. There's either, well, maybe 5. There's the completely impossible, sort of quite rare, roughly equal, really very common, and always happens. And human beings, when you talk to them about chances of things happening, they don't really think in numbers. And so that's why it can be quite interesting talking about probability, where you say a 67% probability of something, because most people, that's not any different from a 47%. You just say, well, it's just like, you know, somewhere in the middle. Your natural inclinations with probabilities are not quite as precise as we are when we're being mathematical about it. So there you go. Just cut yourself some slack. Okay. So I'm going to talk about this possibly a little differently to the way your lecturer did, which is the point of these revision seminars, but I'll try and make it match up. So this is my first, and my mantra is that the only way I'm going to write it down, it's so important. The only way to know the probability of one thing is to know the probability of all the things. And this is a thing that I will say to myself and to other people when I'm telling them about statistics. This is David's mantra. Because probability is a comparison between what you want to happen and what could happen, or possibly a comparison between what did happen and what could have happened, or possibly a probability comparison between, no, that's pretty much it. What did happen, you want to compare how often what did happen happens compared to all the things that could have happened, or how often the thing you hope to happen happens compared to all the things that could happen. So well, maybe you don't want it to happen. What you're imagining happens. You might not want it to happen because it might be a bad thing. So all the things that could happen is the very fuzzy words version of what your lecturer calls a sample space. Sample space is the list of all the things that could happen. That's what she used space, didn't she? Yeah. And if you can break all the things that could happen down into small enough bits, then those bits are called the simple events. So an event is a description of something that could happen, and it can be quite complicated. It can be quite simple, and the sample space is the list of all the things that could happen. And every one of the things that could happen has a probability of its own. And the only way to know the probability of one thing is to know the probability of all the things, because you have to compare the one thing you're thinking of to all the things that could be. That's why. So when you're doing a game and you roll a six-sided die, and you imagine all the things that could happen, the only way to roll a six-sided die once. These are all the options for what could happen. And the only way to know the probability for one of them is to know the probability for all of them. And so we assume if our die is fair that they all have the same probability. And so I say that this must be a sixth of the probability here because they all have the same. That's the very simple idea for how probability works. But it's usually much less simple than that. Okay. Right. Cool, cool, cool. I'm just getting ahead of myself probably, but I'm just talking it through. So these are the outcomes, and these are the probability. But we know they're all a sixth because there's 6 of them and they're all the same. And the one rule that we know for sure is that the probability of everything or anything, like the probability that something happens, is 1. And so since we assume they're all the same, they're all equally likely, and they all add up to 1, they have to each be a sixth because there's 6 of them. And this is the beginning of probability. This is where people start. And it's really interesting that the beginning of probability is already in lecture 3 of the sequence on probabilities. This is called a random variable. It's a number. It's not always the same number. Sometimes it's one number, sometimes it's another number, but each number has its own probability. And so if I said that x equal number rolled on a 6-sided die, then this x could be lots of different numbers. I roll it once, now today it's 3, roll it another time, now it's 4, roll it another time, now it's 1, roll another time, now it's 3 again. Different numbers, different times. But if I'm imagining all the numbers it could be and how likely they all are, that's a random variable. So most of the things we're interested in economics and life can be recorded as a number if we want them to be. And people have been studying probability for long enough to have names for the different arrangements of probabilities. So this list of all the probabilities for all the options is called a distribution. So with a die, the distribution is that all of the numbers have the same probability. But when you roll dice twice, different numbers have different probabilities, and that's a distribution as well. The word distribution in English means how the probability, or not probability, distribution means how things are spread out. You can talk about the distribution of koalas in the South Australian bush. And so that's telling you where are there more, where are there less. And so when we talk about the probability distribution, it says where is there more probability, where is there less probability. So when you talk about a description of all the options and all their probabilities, it's called a distribution. Technically a probability distribution. Okay, I'm getting ahead of myself though, but I just wanted to show where we're going. So what we really want is to be able to describe the distributions of things. Because even though a particular number, you might not know what it is every time you do it, some numbers might be more likely than others, and that's useful information. So when you roll 2 dice, the most likely number to roll is 7 in the combination of the 2 dice. And it's really unlikely to roll a 1, or it's impossible to roll a 1. It's really unlikely to roll a 2. It's really unlikely to roll a 12, but it's really quite likely to roll a 7. And then all the other numbers have their own probabilities. And so because you know all the probabilities, you know what to expect. And the normal distribution is a classic distribution for things that you measure on individuals rather than write down with a die. So if you built, it comes up in quality control a lot. And you have a factory, it makes ice cream in tubs of 2 liters. They might not really have exactly 2 liters in every tub. And so you just want them to be 2 liters on average, possibly more likely to be more than 2 liters than less, so that the people don't get upset at you. Not that anyone's going to measure it, but yeah. Or maybe if you're the kind of business owner, you may want it to be more likely to be less than more, so that you don't, anyway. But it's still 2 liters on average. And so distributions are important. And the only distribution with a name that you've been given in this course is the normal distribution. But there are others. There is the binomial distribution as well. And there is the T distribution, which you've been told about as well. And different kinds of situations have different arrangements for their probabilities. And if you're very lucky, statisticians and probability theorists have already given a name to that distribution. How are we feeling? All right. Okay. Okay. So an event is, I know what an event is. It's a thing that happens. So when I describe that in ordinary English, an event is a thing that happens. I talk about going to a concert, that's an event. I talk about tripping over a banana peel on the ground, that's an event. That has actually happened to me, slipped on an actual banana peel. I couldn't believe it. Yes, depends on how long they've been rotting for. A fresh banana peel is quite sticky and you can't slip on it, but a several-day-old one, that's a whole different story. But I actually slipped on a banana peel. So an event is a thing that happens. So this is what I'm imagining it is. This is what it is in English, right? That's what it is in English. That's what I'm thinking. But in probability theory, we have to be more precise because it's maths. And maths is very precise. And so we say an event is, what is it, a collection of outcomes? I believe that's what it is. I'm just going to check that. Just give me a second. An event is any collection of one or more possible simple events. You can't define event by using the word event. Honestly. No wonder people took centuries to figure out the details of probability if we got crap like that. Sorry. So a collection of outcomes. And you have to decide what an outcome is, which is also a thing that happens. So it's all very vague, unfortunately. But in most of the time, the way it turns out is that there's a description of the thing that happens, which you can unambiguously decide whether the thing happened or not. So you have to be able to decide. So here's the problem. A collection of outcomes is mathematically a set. That's what a mathematician says a collection of things is. It's a set. And the rule for being a set in maths is being able to decide if you're in it or you're not. And the decision that you make about whether it's in there or not can usually stand in for the name of the set. So I just want to point something out. Do they use P with brackets for probability or PR? P, okay, cool. That's another difference that's in different courses. So you can say the probability of, you know, rolling an even number on a die, and it's literally just a sentence. Yep. For example, and that's okay. You can have a sentence, or you can actually, you know, or you could say X is the number rolled on the die. And say the probability that X is equal to 2, 4, or 6. And that's okay as well. That's a perfectly good sentence that describes a collection of outcomes. Or you could say the probability of the set of numbers 2, 4, or 6. So this curly brackets here is a way of mathematicians writing a set. So when a mathematician writes a set, they use curly brackets. Or you could have said, you could have given the letter A to represent the set on the drawing. And so you could have said, you know, two, 4, 6, and then said the probability of A. So these are all ways that, people talk about probabilities, and these two are different to these two. I mean, they mean the same thing, but this is the name of a set, and this is the rule for deciding if you're in the set or not. And we both allow them, and it's really quite vague, right? Because this is P and you put a sentence in this spot, and this is P and you put an object in this spot, which is a set. It distresses me, but we're all used to it now. So I just wanted to point that out because all of the notation for combining events together belongs here in this land, where we have sets and we make new sets out of them with Venn diagrams and stuff. And it belongs here, but you can't interpret the statement you have directly about the thing you've got here directly about statements. You have to be very careful about how you do it. So just wanted to point that out. Okay, So that's cool. So if events are sets, we can borrow some of the things that mathematicians invented for set notation and use them for events as well. That's what I'm talking about. So you can say A intersection B, which is so if A was A is a set of even numbers and B is a set of numbers more than 2, then A intersection B would be the set of even numbers more than 2. Or if you like, numbers that are even and more than 2. And so this is a description of the set. And so when you do A intersection B, when you combine the two descriptions together, you end up with an AND, basically. But when you do a drawing of the set, it's not combining the sets together, it's overlapping them. So you would have, this is A. Actually, I'm just going to draw a better picture than that. So here are our numbers. So this is A, that bit there. And this is B. And then A intersection B is the 4 and the 6. This bit here, where they overlap. So it's much more common for you to see it like this, right? You go A and B, and this bit there is A intersection B, like that. This is called a Venn diagram. So this notation here is borrowed from set theory, but it's most common when you write probabilities to think of them as descriptions of what could happen and to not think of them as sets at all. And so you would think of A as the statement being an even number and B as the statement being more than 2, and then A intersection B would be being an even number and being more than 2 at the same time. How are people feeling? So if everything's equally likely, then it looks to me like the intersection has a smaller probability than either of the other ones. Like there are more options for how A can happen than A intersection B can happen. Right. Moving on. About it. But not everything has to have the same probability, and so sometimes it's a little difficult to tell. Like when I have the numbers on dice, on 2 dice, 7 is much more likely than other things, and so not necessarily just counting how many options there are. Okay. All right. So this one is a union B. Then what that would mean is that if you have a set A and it has a description, you know, for what it means to be in A, and you have a set B and it has a description what it means to be in B, then the set A union B, the description is being in A or being in B. And so this union here, when you look at the description, it tends to produce an or in the description. But what it looks like is that that's A and that's B. And A union B is all of this stuff. So in the example I gave before, if A is being even and B is being more than 2, the union is being even or being more than 2, which is actually everything except 1. So if that's even and that's more than 2, when you combine all those together, that's everything except 1. Yeah. Because this only works for our die, like if it was something else, then it'd be different. Yeah. Okay, cool, 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 cool. And then there's other ones as well. What is the other ones? There's complement. Complement of A. That's how your lecturer did it in the notes, as far as I could tell. And it's not A. So if you've got set A with description, being in A, then the set A complement is the description is not being in A. Yeah, that's pretty much it. And then there's this one. Did she call that minus? I find this one confusing. I normally read this aloud as A without B. Or A yeah. Just want to draw the picture. If that's A, then that's A complement. It's everything except A. But A without B is if that's A and that's B, then A without B is the part of A that's not in B. And so the set A without B is like, the description is in A, but not in B. I don't know if it came up much, it was in the lectures. So in our example with the numbers, 1, 2, 3, 4, 5, 6, A was this and B was this. So A without the bit that's in B is just the number 2. Which means being an even number but not being more than 2. And the only even number that's not more than 2 is 2. So A was being even, B was being more than 2, and A without B is even but not more than 2, which is just the number 2. So yeah, the but not is how you put the sentences together. Cool. So it turns out that like language constructions like and or and but not turn into set constructions in the drawing. And there's all these probability rules that go with these things. Yeah. Cool. I'm going to stop there for a moment and just chill for a second while people write things down. Well, I like having them all lined up on several sheets rather than, yeah, I like it. I'm excited by this. I haven't written it that way before. Okay. I just want to do an example, like the most common. I just want to, not an example, but I just want to talk it out a bit. If your sample space is a collection of numbers, like the numbers on a die, or the number of children that somebody has, or the number of times they went to the Maths Learning Centre in semester 1 or whatever. If your sample space is a collection of numbers, then most of the statements you can make about it are math statements. And so if x equals the number of, excuse me. Okay, here's a thing. When you do probability, you have to know what object is having information recorded on it. So when you do a normal distribution, you need to know what is it. It measures height, and you're going, which people? Is it all people? Is it children? Is it students of Uni of Adelaide or whatever? You have to know what objects are being used to measure things. And so that's always something that should happen. It hasn't happened in the lecture material, but it's really important if you ever define one yourself to say what belongs to it. So you might say, consider a student at Uni of Adelaide, and let X be maybe a random student, but that'll do. They visit the MLC in semester 1. Okay. MLC stands for Maths Learning Centre, by the way. That's just what's on my mind at the moment. And so you could ask yourself the probability of X being greater than or equal to 5, for example, that they have at least 5 visits. So this thing is a statement about the number X, and I can turn that into a statement back and forth into a statement about things. I could say the probability that a student visits the MLC in semester 1, that's what X is. Actually, just a second. The number of times a student visits the MLC in semester 1, that's what X is. That's exactly what X is. I've replaced it with its word, is at least 5. And so you could say that as visits the MLC at least 5 times in semester 1. So this is a grammar problem. Probability is at least a quarter grammar. You can turn a statement like this. What's the probability that a student visits the MLC at least 5 times in semester 1? And go, okay, that means that the number of times they visit is at least 5, and X is the name for the number of times they visit, and greater than or equal to is a symbol for at least. And so, not that I know what this probability is. It's much less likely than visiting once. But you can turn statements about objects into statements about numbers. And that's a really important thing to be able to do. But now I can think about, I could say that A, B, then that X is greater than or equal to 5, then a complement is the event that X is less than 5. So A is the number X being 5 or more. A bar, the complement of A is the event that X is not that. And so it should be possible to turn things one way or the other with numbers. And these two events are called complementary events, but importantly, they're also a special kind of event, which is that they are exhaustive. That's the word they used. These are exhaustive. So one event and its complement together are called exhaustive events. They cover all the possibilities. X is either going to be 5 or more, or it's going to be less than 5. There's no other thing that it could possibly be. Sorry about that. No other thing it could possibly be. And so together they are exhaustive. But you don't just have to have two events for it to be exhaustive. So and so what they mean by exhaustive is it covers everything. It covers all the possibilities. And the word exhaust means to run out. And so when you look at both of those events together, you run out and you know, you run out of events to consider. You run out of possibilities, you run out of outcomes. It exhausts the list of outcomes. That's what that word exhaust means in this context. My father has a book called an exhaustive concordance. A concordance is a list of the words in the Bible, and he has an exhaustive concordance because it lists all the words in the Bible. It's also like 2 kilos. Like it's a, anyway. Yeah. Yeah. So dictionaries do not claim to be exhaustive. They do not list all of the words in a language, but they try. Okay. But you don't have to have A and A bar to be exhaustive. You can have 3 things together that cover everything. So as an example, I could say X is less than 5 and X is between 5 and 10 and X is more than 10. Those 3 events are exhaustive events. Yep. And they're also mutually exclusive events. They don't overlap. You can't be less than 5 and more than 10. And you can't be between 5 and 10 inclusive and also be more than 10. So these are mutually exclusive and exhaustive events. So it is possible for events to not be mutually exclusive and still be exhaustive. So I could have these 2 events. X is at least at most 10 and X is at least 5. Together they cover all the options for what X could be. It's just that they cover the ones between 5 and 10 twice. And so they're not mutually exclusive because they overlap. It's possible to be less than 10 and more than 5, but they are exhaustive because they cover all the options for X. And just as a picture, these are all my numbers. Damn it, that's bad. Sorry. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. These are all the numbers that could be. And here we have the 3 sets. This is less than, oh, that's less than 5. And that one's between 5 and 10. And then we've got, you know, there's lots of numbers over here. Whereas this one, this is less than or equal to 10, that's this bit. this is greater than or equal to 5, that's this bit. They have an overlap in the middle, and so they're not mutually exclusive. Mutually exclusive means they don't overlap. Damn it, just a second. Events are mutually exclusive if, or when, I guess, when they can't happen together. They can't happen at the same time, which means that as sets, they don't overlap. So this is the language version of what mutually exclusive means. Mutually exclusive means A and B when A intersection B. I just want to check something. And there it is. Okay. When A intersection B is equal to the empty set. So your lecturer used this notation. It's a 0 with a cross through it. It's not the letter phi, not the Greek letter phi. It's a 0 with a cross through it. And so this is the name of the set which has nothing in it. So this is short for saying A intersection B is the set with nothing in it, meaning A intersection B is nothing. There is nothing in the space between them. And so these two, there's nothing in the gap, they don't overlap. There's nothing in the place where they don't overlap. When I try and do the intersection, there's nothing there. Whereas this one, the intersection contains all this stuff. And so that's what mutually exclusive means. Okay. So when you think about just descriptions of things, is the event of having a possum in your roof mutually exclusive from the event of having a cat? The answer is no. It's possible for you to have both a cat and a possum in your roof. But if it's impossible for things to happen together, then they're mutually exclusive. Yeah. Is it possible to roll both an odd number and an even number on a die? No, they're mutually exclusive. They don't happen at the same time. It's not to say that they can't happen. They're just not allowed to happen together. Yeah. Okay. So that's combining sets. We haven't even talked about probability yet. Probability is, well, add up the probability of all the bits. And knowing that everything adds up to 1 tells us already the rule for exhaustive and mutually exclusive sets. The probability of x being less than 5 and the probability of x being greater than or equal to 5, these two events are mutually exclusive. And not just that, they're exhaustive. They cover all the possibilities. This one is the complement of that one. And so that probability is guaranteed to be 1 because all the probabilities add up to 1. I don't even need to know what x is. Like x could just be anything. But these two statements cover the entire universe. Whatever x is, it's either less than 5 or it's greater than or equal to 5. And so these two possibilities, together, their probability must be 1. So that's just an example. And the way you normally do it is that you would normally see it more like this. Something like that. Do it as a 1 minus. So that's the rule is that the probability of A complement plus the probability of A must be 1. Which means that the probability of A complement must be 1 minus the probability of A. because together they add up to 1. And so probability of A complement must be the gap between them. Yeah. So this is true. And it's common when you first learn probability to do it with the letters A and whatever. But by the time you start talking about normal distributions, all of your probability statements will look like this. And that's why I wanted to talk about them now. Yeah. So that's our first rule. And it doesn't have to be A and whatever. If you know, if A and B and C are mutually exclusive, and exhaustive, then the probability of A plus the probability of B plus the probability of C must add up to 1, because they add up to everything. I know that that's not a rule that you've been told, but it's the truth. You don't have to, this is the universe, and this bit's A, and this bit's B, and this bit's C, and their total area is 1. That's the idea behind it. Okay. I am absolutely certain that you've probably been told a rule about how probabilities with intersections and unions interact, have you? No. Oh, okay. Cool bananas. Good-o. That's fine. Let me just check probability number 2. I really should just download them, but here we are. No, you have not. All right then. That's in another course. In another course, you get given this formula. I'm just going to write it down, but the probability of A union B is the probability of A plus the probability of B minus the probability of A intersection B. Have you seen that? It's not in those slides. I couldn't find it. Maybe it is in those slides. I just missed it. So this is the other rule. And they don't have to be mutually exclusive. For any events A and B, this is always true. They don't have to be mutually exclusive. They don't have to be exhaustive. This is just the truth all the time. And the picture that goes with it is this. So this is A. The probability of A is that area. And the probability of B is that area. And when you add those two areas together, the bit in the middle, you've counted it twice. And so you have to take it off if you just want the total area of this bit. And that's the answer. So if you go, the probability of A is this area. Probability of B is this area. And we've counted the probability of A intersection B twice. So we have to take it off to get to the total area of the A union B. And that idea of area being probability is a really useful idea. When you look at a histogram, the taller heights of the bars go with bigger probabilities. Yeah. Cool. So this is the big rule. I believe this is called, no, I don't know what the name for this is. There's a rule for how complements interact with unions and intersections as well. But this is the big rule for figuring things out. Any thoughts or questions you would like to add at this time? Okay. I do have a question of you. The sorts of quiz or multiple choice questions or tube questions you've had about probability and this intersections and unions of things, were they the sorts of things where they described a story of like cards or dice or people or something and then asked you to figure out probabilities afterwards, or there was like a table like in the lecture notes?
Yeah, in the slides there's
yeah.
That was that example used in the lecture for computing probabilities of
Yeah.
such or others. And then in the second assignment, where we had this conversation, there was very similar thing with the example. But yeah, it's basically the probability we started out with all dice and then went on to more complex.
Yeah. Cool. I'm going to just have a look at one of the things I was sent now. I'm just going to write it down, but I just need to find it first. No, I'm not. I'm just going to share on the screen. Okay. So I presume this is one of the quizzes or something. So this is really badly written. I do not mind going on record of saying such a thing. So A is child without a sister, B is child with at least one sister, C is child with an older sister, D is child with a younger sister. So I'm hoping there was text to go with this somewhere, but maybe not. This is just the total information. Okay. There should have been a story, right? There should have been, consider choosing a child from a class of students or something, from a school class. And let A be the event that the child you choose is without a sister. Okay, so even before reading any of the stuff that goes with that, I can see that not having a sister and having at least one sister, together they cover all the options. Like you either don't have a sister or you have at least one. Like they're the only things that could happen. So those two sets are complements of each other. The complement of not having a sister is having at least one. So B is A bar and vice versa. So those two sets are mutually exclusive and exhaustive. And I also know that having an older sister and having a younger sister are not mutually exclusive. It is possible to have both. It's possible to have an older sister and a younger sister. It's possible to have neither. And so they're not exhaustive either, because it is possible to have no sister. So these three, A, C, and D, they are exhaustive. They do cover all the possibilities, but they're not mutually exclusive. Like A is mutually exclusive from D, definitely. You can't not have a sister and have a younger sister. And A is mutually exclusive from C, but C and D aren't mutually exclusive. But together, the three of them are exhaustive because together they all cover all the possibilities. Okay. So A, B, and D, are they exhaustive? Well, A and B are exhaustive all by themselves. It doesn't matter what D is. A, B, and D will be exhaustive, guaranteed. So that's why it says are exhaustive, because together those three cover all the possibilities. And so presumably you have to choose a word from a list. So I could have A, B, and anything else, and it would be exhaustive automatically because A and B are. So the events B and C are mutually exclusive. No, that's not true. You can have at least one sister and have an older sister. In fact, you would have to have at least one sister in order to have an older sister. They're not, in fact, C is contained in B. Like you can't have C without B. So they're definitely not mutually exclusive. It's possible for them to happen together, so they're not mutually exclusive. So this question was asking you to look at the sets and make a decision of what word goes in that spot to make it true, I think. But that was just my guess. It was a bit vague. And then B is or is not a simple event. I can't find a definition of the notes of what a simple event even is. Now, I think that it is. because the lecturer slide said that if you can have a collection of events where they're all mutually exclusive and they are exhaustive, then you can call them simple events. And it is part of such a list. But I think what she's meaning is that if we imagine this as being pitched in terms of a number, like how many sisters do you have, then the simple events are 0, 1, 2, 3, 4, whatever. And having at least one sister is combined for several different options. So I think that's what she's getting at, of not being a simple event. But I can't be sure. That's the one that confuses me the most. Yeah, sorry about that. The set S, which contains the set C and D, is not the correct sample space. The fact that she said the makes me think that there's supposed to be a thing, but I also know that she's French, and so sometimes she says the when she means a. Articles in English are really difficult for people who don't speak English when they're born. Yeah, articles are one of the most difficult parts of English. If you come from a language with no articles at all, it's really hard. And French, they just don't have the word a. So I think she means, is it a sample space? Could it be seen as a sample space? Mostly a mathematician would say the word valid instead of correct. So I think that when we look at C and D, they are not a sample space, because a sample space has to be made of events that are exhaustive and mutually exclusive. And they're not mutually exclusive, and they're also not exhaustive. So it's not a sample space. But A and B could be a sample space. And A and C and D could be no, they couldn't. Nope, ignore that. A and B is the only things that could together be a sample space, because they're mutually exclusive and exhaustive.
If you were to add, so let's say A, B, and D,
yeah,
that would not be
correct. So they're not all mutually exclusive with each other, and so it's not a sample space. That was excellent reasoning. So this is a really great question if you get to talk to someone, what the hell? If you get to talk to someone about it, then this is a really good question to really get at the handle of what the edges of those definitions are. But if you don't get to talk to someone about it, it's not a good question. Yeah. So I think that this question helped me to figure out what exhaustive meant and what a sample space meant to her, but it didn't help me figure out what a simple event was. So I still don't know. But my guess is that if you can pitch this to be about the number of things, then a simple event would only refer to one number at a time. Yeah. Whereas at least one refers to several different number possibilities. So that's my guess. Whereas without a sister is the number of sisters is 0. And an older sister is a whole other thing. You could say, oh, well, that's a whole other thing. So yeah. Oops-a-day. Tried so hard to not get people's names in the video. Just takes me hours to deal with that. Okay. So I have one last thing to mention before I stop talking about that, which is conditional probability. There is another thing we can say inside a probability that we can't say about sets, which is this. Probability of A given B. Possibly with a comma there. Probability of A given B, you need to have a pause there. This is where we start to get really interesting with probability. Technically, no probability, you have to know what all the possibilities are when you talk about a probability. You have to know all the things that could happen. And so different situations, different things can happen. And so that's what this is about. This is saying if I only consider the situations where B is happening, what's the probability of A then? if I compare the probability of A happening to only the things that happen when B happens, what's the probability now? And so you can change the list of things that could happen. And that's what this is. And so in my head, it's like this. This is like you've got A and you've got B. And then in this story, this box is all of the things that could possibly happen. And so you've got the probability of A is the area here. But then when we do the probability of A given B, we just ignore everything that isn't in B. And we go, the probability of A given B is the area here relative to the area of B. That's what that is. So we're going to consider B as the entire universe and call that 100% instead of calling this 100%. And so it may be that A takes up more space in terms of B as a percentage than it does in terms of everything. And so it's really hard to draw in a Venn diagram, but I can draw it in a Venn diagram where they're boxes instead of other things. That's bad. So this is going to be my A here. I shouldn't have done 25. That would be bad. I'm going to do 20 if that's okay. There's 20 boxes and A is going to be this. So I'm going to have A, like that. 8 out of the 20, which is what, 40%, I think? Yeah. And then my B is going to be this. Like that. So in this picture, the probability of A is 8 out of 20, which is 40%. And the probability of B, oh, I didn't want to do that. I'm going to do this. Probability B is 10 out of the 20, which is a half, like 50%. I can see in the picture here that the probability of A intersection B is 4 out of 20, which is 20%. I'm just doing this. And I can even do the probability of A without B, which is this bit here, if I want to. And that's the same as the probability of A intersection not B. They're the same thing. Also 4 out of 20. Cool. But I can do lots of things. But when I do want to do conditional probability, I need to imagine that all there is B. And so when I look at the drawing, when I'm only looking at B, probability of A given B is 4 out of 10, which is 40%. Yay, that's how it works. Whereas if I had the probability of B given A, that's 4 out of 8, which is 50% again. Now, it is a coincidence that the probability of A back here when I considered everything was 40%, and the probability of A given B is also 40%. What that means is that the events A and B are independent. That's our final word that we add to our list of terminologies. That A takes up 40% of all possibilities. It also takes up 40% of B. So considering all the things that could possibly happen, A happens just as often as just considering the thing only B happening. What people normally say is that the event B does not affect the probability of A. But I want to draw another picture to show what it would mean if they weren't independent. This was one example. I'm going to put A in the same spot. I'm still going to make B half. I'm still going to make B 50%. But what if I moved my B's around a little bit and did them here? Like that. There's still 10 B's, right? It's just a different shape than it was before. So the probability of A is still 40%, and the probability of B is still 50%. But when I look at A given B, it's the same. Oh, damn it. That was bad, wasn't it? It's still 4 out of 10. Oh, it's so beautiful. I'm just going to put the B over here. There we go. Right, there we go. That's my B. It's that shape. And the probability of A given B is now 3 out of 10, which is 30%. A takes up just a little bit less percentage of B than it takes up in the whole world. And you could imagine drawing this diagram in lots of different ways and being able to have something that was 40% for A and 50% for B and having any possible arrangement of that. It should be possible by putting my B's in just the right spot to have pretty much any probability for A intersection B. Yeah, down to 0. You could even have A completely inside of B. And that's the thing. So that's called being independent. And I just want to say that probably B given A is 3/8, which is 37.5%. Yeah. So that's my favorite fraction, by the way, 3/8. It's how many liters of milk there is in a glass and a half, and therefore in a block of Cadbury chocolate. Also in a Coke can. That's one of the reasons why I like it. It's just you've got to pick a favorite, so that's the one. My favorite number of all is 65,536. There are many reasons why. It says maths isn't finished yet. 65,536 is the only known power of 2 that does not have a power of 2 as one of its digits, but we don't know for sure. Yay! It's also the maximum number of rows in an Excel sheet. Okay, or it was. Okay, so you can imagine having a two-way table and calculating these things. But that just leaves a definition for what that is. So this is called a conditional probability. I should have said that earlier. Did I write that? Conditional probability on the thing? Oh, yeah. It's called a conditional probability because this is the condition. Technically, all probabilities are conditional probabilities because all probabilities are calculated assuming something. But, you know, that's fine. So also, there is a thing called independent. A and B are independent when the probability of A given B is the same as the probability of A. Or the probability of B given A is the same as the probability of B. It doesn't really matter, it's the same thing. Or the probability of A and B, like A intersection B, is the same as the probability of A times the probability of B. This is very rare for this to happen. But if it does, then they're guaranteed to be independent. So when I go back to here, in this one, 40%, 50% of 40% is 20%, which is not the probability of A given B. It's not the probability of A and B, because A and B is 60%. Not 60%, sorry, 15%. 3 out of 20, 15%, yeah. Whereas in this one, 50% of 40% is 20%, and that is the probability of A intersection B. So if you multiply these two probabilities and you get that one, then you're guaranteed for them to be independent. But if you don't know they're independent to begin with, you can't just multiply those probabilities. That's just not, you can multiply them, but it won't be the same answer as A intersection B. So that's really important. So there are probability problems in textbooks and exams and that sort of thing that I've seen where it said, here's a situation with A's and B's, A is this event, B is this event, and they've explicitly told you that they're independent and then said, what's the probability of A union B? So just an example. Suppose A and B are independent and the probability of A is like 0.3 and the probability of B is 0.6. Find the probability of A union B. This is a classic problem. And so since they're independent, that means the probability of A intersection B must be the same as the probability of A times the probability of B. Because they're independent, B must happen 60% of the time, including the 60% of the time that A happens, like 60% of the time that A happens. And so the probability of A and B happening at the same time, first A happens and then 60% of that time is when B happens as well. And so we get 0.18. And so because we know what A intersection B is, we can find what A union B is. And so A was 0.3 and B was 0.6 and A intersection B was 0.18. And so we'll get 0.9 minus 0.18, which should be 0.72. Not that anyone needs to know this probability, but you can figure it out now. Yeah. Okay. And so you could also have something that says, people are asked if they like dogs. and or cats. Okay. And so we can have dogs, like, not like, cats, like, not like. Let's see, what are we going to have? We're going to have like 100 people here and 50 people here and 30 people here and 10 people here. No, I should put 20 people here, then that's it up to 200 and my life will be easier. Okay. Wouldn't it be nice if you could change your exam questions like that? Do not like your numbers, I'm going to use these numbers. So what's the probability of liking dogs given liking cats? Traditionally, you would give letters to the event of liking a dog and letters to the event of liking a cat. That's fine. In fact, it would probably be in a sentence form, right? It would probably be like this. It would be dogs given that they are already like cats. From this group of people, of course, you know, we don't know if it's true for all people, but true for these pretend people that I made up. And so you would normally say something like, let D be the event that a person likes dogs, and C be the event that a person likes cats. Oh, I forgot to write something earlier on the page. This is the formula. A intersection B is probably, A given B is A intersection B divided by B, but the probabilities of them. When I was doing my diagrams, it was literally the sizes of the sets. But I could just as easily have in this here said, I said it was 4 out of 8, but I could have said it was 20 out of 50, and that would have been the same answer. I do it with the percentages. Yeah. Okay. Sorry. So there are many ways I could do this, but I just want to show you that I could do both. So in this story, what we want is the probability of liking dogs given that they like cats. That's what we want. So I could do it directly from the data here. I could say that there are a total number of people who like cats. No, I'll just do it. I'm just going to calculate all the things instead of doing the short version. The probability of C, damn it. I'll just calculate the totals. So we've got 130 people here, we've got 70 people here, and 200 people in total. We've got 150 people here and 50 people here. Okay. So the probability of liking a dog, given that you like a cat, there's 130 people who like, no, there's 150 people who like cats, and out of those, 100 people like dogs. So I can literally do it directly from the table if I want. The probability of D given C is these, it's out of the 150 people who like cats, and there's 100 of them who like dogs as well. Ta-da! It's like 1/3. 2/3. Sorry. Yeah, there's 3 150s here and there's 3 50s here and 2 50s here. So if you really want it as a decimal, it would be 6, 6, 7 to 3 decimal places. So that's the short version. I could have done it directly from the table. Total number of people here, total number of people in both. That's fine, because given C means that's my table actually, because I'm ignoring all the people who don't like cats. All right. So we want that, but I'm also going to add an extra question. Is D, so are D and C independent? Well, the only way to know if D and C are independent is to compare probability of D given C to the probability of D. So the probability of D is 130 out of 200. There's 130 dog likers out of 200 total. And to compare them, this one's only out of 150 because I'm only interested in the cat likers. This one's out of 200 because I'm interested in everybody. And so the answer is no, they're not independent, because this is different to that. Pretty close though, but not quite. Any difference whatsoever, not independent. Yeah. I could have done it the long way. I could have figured out all of the probabilities if I wanted to. I could have said the probability of D and C, just to point out that it's possible. D and C is 100. And this is, there's no given here, so it must be compared to everybody. Like the probability of dog liking and cat liking is these 100 people are both, and it's not given anything, so it's out of everybody. And so that's 50%. They like them as decimals, don't they? Or do they like as like 0 point as opposed to 50%?
Yeah.
Yeah. Anyway, so I could have figured that out, and I could have said the probability of D given C would be the probability of D and C divided by the probability of C. So I could have figured out those things separately. My cat likers were 150 out of 200. Sorry, that's right, isn't it? Yeah. Which is 3/4, isn't it? Okay. And so this would have, could have been 0.75, no, 0.5 divided by 0.75. And that's also 2/3. So I could have done it that way. Read your, I mean, you know, your lecturer is giving you a multiple choice test, so they don't care how you did it. Do whatever they want, in which case I would do this way because it's much shorter. Yeah, but just to point out that this is a thing that you could have done. And you can imagine a written assignment question that asks you to calculate all these things. And if you've already gone to the effort of calculating these, you might as well just do this. Yeah. Right. And since they're not independent, I can't multiply the probabilities to get the probability of the intersection. And all I can do is just write them down from the information I've got. But if they told me in advance that they were independent and gave me part of this table, I'd be able to figure out the rest. So if they told me this part of the table and said cat liking and dog liking are independent, then I would have said, oh, 2/3 of the dog likers like cats, which means that 2/3 of the people must like cats. And so it should have been possible to figure out some of the other bits of the table. Maybe they give me the 2 anyway. Yeah. So, and yeah. Yeah, 2/3 of the cat likers like dogs. And so that means that 2/3 of the people must like dogs. And also I know, yeah, so maybe not quite enough. I probably need at least one other number somewhere, and then I can figure out the rest. Yeah. I have to think about that. Think about that. Yeah. Okay. Cool. How are we feeling? That's quite enough talk about probability, but I'm glad that we did this today. Like there's a lot going on here. Yeah. So in the lecture slides, they had a table like this, and they figured out all of the various probabilities that you could possibly figure out, didn't she? That was that. There was M given M intersection T bar, and like, yeah. Yeah. Cool. Yeah. I remember the day that I suddenly realized that mutually exclusive and independent are not the same thing. And they go on about it, but independent is a referral to how the probabilities change from one to the other. Mutually exclusive is the chances of them happening at the same time is 0. And that is the worst kind of not independent, because knowing that B happens completely and utterly changes the probability that A happens. It becomes 0. So yeah, cool. The reason I just want to say something. If you Google the meaning of independent for probability, sometimes you'll get this and sometimes you'll get this. Just be careful. I don't know which one's in your course. I think it's this one. That one there. Which is one that makes most logical sense in terms of the meaning of the word independent in English. But yeah, I just wanted to point out that if you Google any of this stuff, you will get things that are different because everyone does probability differently. So just be careful to, when you Google, match it up with what the lecture slides said. All right. Any other thoughts or questions about probability before I close off the revision seminar? Sweet. Just thinking, because I've got 5 minutes, so. Just want to do one more probability thing. And it's way out, but you mentioned normal distribution, so I want to do it. Suppose the height of guinea pig can jump is normally distributed with mean 15 centimeters. No, let's go 10. They can jump pretty high, actually. And standard deviation. Um, 2 centimeters. Okay. Guinea pigs are on my mind. We went to the Gorge Wildlife Park on the weekend, and they've got a little guinea pig enclosure with about like 100 guinea pigs in it. Yeah, when guinea pigs get together, they jump. They call it popcorning because that's what it looks like. Okay, so suppose the height guinea pig can distribute with mean 10 centimeters and standard deviation 2 centimeters. They can't jump sideways at the same time. They can jump vertically. So, so you can have quite low fences for guinea pigs because they can't jump sideways at the same time. So. And why would this be in an economics course? Well, you might be selling guinea pigs. What is the probability? You can always pitch anything to be about economics by saying, oh, it's a marketing thing. What is the probability that a guinea pig, oh, damn it, can jump over 15 centimeters? Okay. This is a probability question. It's definitely a probability question. It asks, what's the probability? But you have to know what all the possibilities are and how likely they all are in order to answer any probability question. With our cat and dog likers, we had all the possibilities listed there. We have every person and which category they belong in. With this, they've told us a normal distribution, which is enough to tell me all of the possibilities for how likely it could be that, for what a guinea pig could jump and how likely they all are. Technically, it's not really normally distributed because normally distributed, you have to be able to get any number, including the negative ones, but it'll do. So we want to make statements about probabilities. We want to write like P brackets, and it would be easier to make that statement if I gave X the name of the thing that I'm measuring. That X be the height a guinea pig can jump. Then what we want is the probability that X is greater than 15 centimeters, in centimeters. And the only way to know that is to know the distribution. And so we can say that X is normally distributed with mean 10 and standard deviation 2. Okay. Did your lecturer write this with a twiddle? No? Okay, that's a maths thing. Over in maths, they have a symbol for is distributed according to, and they would say X is distributed according to a normal distribution, 10 and 5. Okay. But you don't have that in your course, so I won't put that there. Okay, and what that means is that if I look at all the possibilities of what X could be, and I draw a curve to represent which ones are more likely than which other ones, it would look something like this. And this would be 10, and this distance here would be 2. And so my 15 is like way over here. That bit just there. These bits, this bit, there's the 15. This bit is the bit I'm interested in. These are all the X's that we're talking about. And the probability that goes with them is this area. That's how we calculate this stuff. So we haven't drawn a graph like this before in the revision seminar, but that's what this height is for how likely it is, and the area is the probabilities. And so this is a diagram of the area. And so unfortunately, like if I had Excel handy, which I do, I've got a computer just here, I could ask Excel to calculate that probability for me. But I'm pretty sure in this course, you're supposed to use a normal table. All right. So this is great. And I have to compare this area to this area. It's because I'm imagining that this area is 1. So it looks like very small. And that's a very bad diagram. And the problem is that if you have a computer which has got a normal distribution calculated into it, then you can do it. Like you can just totally like. So we went from 15 up to infinity. And it tells me the probability is 0.0013. Great. But not so easy. It turns out that if I multiply a number by like a random variable, which is a normal distribution by a number, then I get a new normal distribution. And it's got the mean multiplies by that. And if I divide by a number, then the standard deviation will divide by that as well. And so what will happen is if I take off the mean, so I'm going to do maths on this statement to make a new statement, which is also true. If I take off the mean and divide by the standard deviation, then it's still the same statement. It tells me the same information about the number x. But I can call this variable z because it will be the standard normal distribution. And this one will be 5 divided by 2, which is 2.5. And so what I can do is I can convert this into this. And it's the same information and the same probability. And I would go and look up in a table what the probability of z being greater than 2.5 is. I don't have a table handy, but give me a second. There was an excerpt from one in the lecture slides. This is a normal distribution table. It says that if we wanted to be for z to be, it says area to the left of the z score. Damn it, my picture's got an area to the right. So I'm going to have to do some work to make that better. That's okay. I can use this table. I'm so excited. My table only gives me bits on this side, and it's perfectly symmetrical with 0 in the middle. So these are negative numbers over here. So that's the same as the probability of z being less than minus 2.5. Yay! And my table says, there's minus 2.5 there. And minus 2.50 is here. If it was minus 2.52, I would have gone across to this bit. And the answer is 0.00621, which is not what my other thing said. I'm very distressed. That was 2.5 there, isn't it? Oh, I wrote 16 there instead of 10. There we go. Cool. It is right. Okay. Let me just do. Whoa. I'm just going to get my calculator. I'd written 16 here, but it's actually 15. And that's the right answer that the table gave me. Cool, 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 cool. I just want to do one final probability notation thing. So you can do things like do maths calculations on the things that are inside the P without affecting it, and turn this into something and say, oh, that's a different distribution, and that's okay. And I could have figured it out as 1 minus the probability that X is less than 15 and used the plus 2.5 side of the table, but only have a negative side. So these are all things you can do, and I just wanted to mention them. Cool, that's enough. I'm going to stop recording.